What's up, guys? Mr. Wicklehouse again, and today we are talking about linear programming. Alright, so this is going to pull together a bunch of things about systems and graphing linear inequalities and all sorts of fun stuff. Let's get started. Alright. Linear programming problems are typically word problems. So they're real world situations. You're trying to figure out a lot of times like what the best case scenario is for something. That being said, there's some terminology or definitions that we need to talk about a little bit so that as we move through this, then you guys will understand what I'm saying. So to start off with these linear programming problems, there's something called the restraints. Now, the restraints are the inequalities and variables in your problem that help to bind your region. In other words, they set up the boundaries or the fences around the area that you're mostly concerned with, and those are the restraints. After you go through and graph the restraints and do all that stuff with that, then you come up with this area that's called the feasible region. That's the area that is created by the intersection of the restraints, and it contains all the possible solutions to the problem. So everything that involves every point, every sale, every whatever it is that you happen to be talking about is all contained within this feasible region that you should be worried about. Okay. Finally, one other thing is called the optimization equation. This is an equation that you'll either create yourself or it'll be given to you to help you find your maximum or minimum for the problem. So like if you're trying to find the maximum profit, you'll have this equation that you'll plug in some numbers into that you get from within your feasible region, and then those numbers will help you optimize either to maximize your profit, minimize your loss, whatever it may be that you're happening to look for. Okay. Alright, that's all for vocabulary, so let's get this thing started. Okay, so we're going to identify the restraints. Just like with any other word problem, we're going to go through and we're going to read the problem. So a manufacturer of ski clothing makes ski pants and ski jackets. The profit on a pair of ski pants is $2 and on a jacket is $1.50. Both pants and jackets require the work of sewing operators and cutters. There are 60 minutes of sewing operator time and 48 minutes of cutter time available. It takes 8 minutes to sew one pair of ski pants and 4 minutes to sew one jacket. Cutters take 4 minutes on pants and 8 minutes on the jacket. Find the maximum profit and the amount of pants and jackets to maximize the profits. Okay, so identifying the restraints. Well, as I'm reading through my problem here, I see something about money, which is important, but that's not what my restraints are. My restraints for this particular problem, I'm really looking at the time that it takes to do stuff. So to start off with my restraints, 60 minutes of sewing operator time and 48 minutes of cutter time. Okay, that's what we're going to be looking at. That's what we're going to use to help us build our inequalities. Okay. All right. So now that I've got that part done, let's think about some other stuff in here. What else do we have besides the 60 minutes and the 48 minutes? Well, I see here that it takes 8 minutes to sew one pair of ski pants and 4 minutes to sew one jacket. And then for the cutters, it takes 4 minutes on pants and 8 minutes on a jacket. Okay. So now all these things together, 60 minutes on a sewing operator time, 48 minutes on cutter time, and then it all ties into the pants and the jackets. Alright, so that being said, that's the important stuff right now. Let's look at how we determine the variables and write the variables and create the restraint equations. Okay, So the variables that we're going to talk about, what are we making? What is the one constant thing through here that affects the profit, the time, everything else? Well, it's the pants and the jacket. Okay, so that's what I'm going to use for my variable. So I'm going to say that X is the pants. And I'm going to say that Y is the jacket. So there's my variables that I'm going to use. Okay. If X is the pants and Y is the jackets, let's think about some things here. Well, when I'm doing this, I need to think about the lower restraints. So what's the minimum number of pants that I can make? Well, you might be thinking 1, but really the minimum number of pants I can make is 0. So I know that my X value has to be greater than or equal to 0. It's going to be a very common restraint when you're doing these things. It may not happen all the time. There may be a minimum value that you're given in the problem, but 0 is going to be very common. Which means that the jackets also, 0 is going to be a lower restraint for those as well. Okay. Alright, so what else? Well, we said before that we have 60 minutes of sewing time and 48 minutes of cutter time. So what we're going to do is we're going to take both of these things into account and how that the pants and the jackets apply to those. So let's look at the sewing operator time first. I see it takes 8 minutes to sew 1 pair of ski pants and 4 minutes to sew 1 jacket. Which means that for the pants, if I multiply 8 times the number of pants that I have, that's going to give me the total number of time to sew pants. I'm going to add that to the jacket, and it says 4 minutes to sew a jacket, so I'm going to do 4 times Y to get the total time to sew a jacket. Well, I know that my total sewing time that I can have, the maximum sewing time is 60 minutes, so that means this equation has to be less than or equal to 60 minutes. Okay. That is the restraint that I'm going to set up for my time on that as it relates to the pants and the jacket. Okay, what's the other thing? Cutter time. Alright, well it says 4 minutes on the pants, 8 minutes on the jacket. That means 4 times X on the pants plus 4 times Y on the jacket has to be less than or equal to 48 minutes, so that's the total time. Okay. Now I have my restraint inequalities set up, and I'm ready to continue on with my problem. You always want to define your variables and set up your restraints. Alright. What is the question asking you to find? Well, as I read through here, it wants me to find the profit on a pair of ski pants and on the jacket is this, and it wants me to maximize the profit because it's looking for maximum profit. So we're trying to maximize the profit. Well, in order to do that, we're going to use this information that they give us on the profit. Okay. And we're going to write that equation, this optimization equation. Many times you'll see it written as some kind of function, but the function is going to be with 2 variables here. Okay, so we'll say f of x and y is going to be equal to, remember we're using x and y. When I'm finding profit, I'm going to be adding dollars together. Ski pants Remember that pants was X, so that's $2 a piece, so 2 for that one. And $1.50 for the jacket, so I'm going to do 1.5 on that one. That's how I'm going to write my optimization equation. I'm going to see what the problem is asking me to find, then see how it relates to my variables. Okay, so there's our optimization equation right there. All right. Now what are we going to do? Okay, well, from here on out, writing the equations and stuff was really the hardest part. Getting all those things, all that information from the word problems in together and figuring that part out. Now all we're going to do is we're going to graph this guy. Okay, so I know that x has to be greater than 0, so that's this. So I know that this is the area that I'm working with. Everything to the right of this. Okay. And then y has to be greater than 0. So right now I've already blocked out these bottom three. Okay, because x is greater than 0 is this way, y is greater than 0 is this way, so I'm just working within this quadrant 1, this first quadrant of my graph. Okay, so that's going to be the area that we're going to be looking for all of this. Now let's do the rest of our constraint, or our restraints. So we've got these. In order to graph these, I want to get this to be y equals something. Okay, so I subtract 8x, divide by 4, so on and so forth. You guys know how to do this. And I end up getting y is less than or equal to negative 2x plus 15. Okay. Now let's graph this. You might be saying to yourself, Mr. Wickelhaus, there are not 15 dashes on here. I don't think there are. Let's look. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Nope. Okay, well let's take it up a notch. Let's do these in threes. So there's 3, 6, 9, 12, 15. So there's my y-intercept at 0, 15. 15 is the y-intercept. 0, 15 is the point I'm going to start with. Got a negative slope, which means I'm going to go down 2 and over 1. That's going to be my first point. Down 2, over 1. There's my second point. I'm going to use some kind of straight edge here. Now I'm going to graph this guy. Okay. Alright, there's that one. Okay. Now let's do the other one. I'm going to go through, simplify this. Again, solve for y. You always want to solve for y to make it easier to graph for you. This is going to be y is less than or equal to negative x plus 12. Okay. That means here's my 12 right here. And I'm going down 1, over 1. Down 1, over 1. Down 1, over 1. Alright, let's graph that guy. Okay. Remember when we graph these inequalities, we got a shade where it's telling me to shade. So this is saying less than, this is saying less than. Means I'm shading down here on this one. I'm shading down here on this one. So my area that I'm most concerned with is the one where everything is overlapping, so it's this area right here. This area right here is my feasible region. Okay? My feasible region. Alright, so now we need to look at some of these points here and find the vertices of where these things are meeting at. You can see there's 1, 2, 3, 4 vertices on this shape, on this quadrilateral that we've constructed. And those are the points that we're going to be most concerned with to help us find our maximum or minimum depending on the problem that you're looking at. So this value down here is 0, 0. Okay. This one over here, this is 1, 2, 3, 4, 5, 6, 7. This is 7, 0. This point right here is 0, 12. This point right here, remember we went down 2 over 1, down 2 over 1. So that's 4 away from the 15, so this is 11, the y value is 11, and the x value is 2, so 2, 11. Okay, so those are important points. So over here, when it says determine the points of intersection, otherwise known as the vertices of the feasible region, those are the points that we're going to write down. 0, 0, 7, 0, 0, 12, and 2, 11. Okay, those are the important points. Now we use these points with our optimization problems. Remember, the optimization problem is this. All right. And we're going to take each one of these and plug them in to help us determine what we will maximize or minimize our question. You know, 0, 0, plug 0, 0 into this. So f of 0, 0, that's going to just be 0. Okay. Plug this one in. That's 7 times 2, 0 in for this, so f of 7, 0 is going to be 14. Look at this one. F of 0, 12. Plug that in, that's 0, 1.5 times 12, that's going to be 18. And lastly, we'll do f of 2, 11. That's going to be 4 for this. 1.5 times 11 is 16.5. So this one, add those together, that's going to be 20.5. We're looking to maximize our profits. Well, this one, selling 2 pants and 11 jackets, is going to give us a profit of 20.5. So, to maximize profit, make 2 pants. Oops, sorry, light went out. We're almost done. This is a long video, I know. 2 pants and 11 jackets for a profit of $20.5. Okay, guys, I know this was a lot. You might want to go through and watch this one again. I know it's a long video, but there it is. That's how you do these. Take a look at them, practice them, do what you can with them. I'll post a couple more videos on this, not by me personally, but just some extra things for you to look at. And of course, you can always come and talk to me if you need help with it. So I'll talk to you guys later.